Okay, thank you, Larry. Welcome back, everyone. So in this session, our next speaker is Margaret Hartley, and she will talk about what do observational researchers need codes to do. And she will be talking remotely. Margaret, you can share your screen if you want to.
Okay, great, thank you. I was asked to talk about what observational researchers need volatile models and codes to be able to do. So I want to break this down into some subsections. I'm going to start by thinking about what kinds of data observational researchers might be working with, which I hope will be familiar to everyone in the room. Then I want to think about the kind of practicalities of using models and codes. Then I want to show you maybe a very non-exhaustive list of some examples of the kinds of calculations that observational researchers might want to do, and then some thoughts on future developments. I'm aware that in 20 minutes I can't cover everything and all the ideas that people might have, so I hope that you can use these remarks as a springboard for the discussions that are going to be happening in a few minutes' time. So first off, what kinds of data we're working with. Mostly I'm working with petrological data. That is, we're taking natural samples from the field, silicate glasses and crystal-hosted melt inclusions, and we're measuring these by a variety of geochemical techniques. So our input data for volatile solubility models will almost certainly involve major elements, may occasionally involve trace elements, and of course, we want to measure the volatile species themselves. Water, CO2, sulfur, fluorine, and chlorine are fairly straightforward to measure by a variety of electron probe, SIMS, FTIR, and in some instances, we can even start measuring more exotic volatile species like bromine and iodine. And of course, we might want to be measuring these kinds of things in experiments as well. The second kind of data that we have access to are observations of gas data, gas compositions and gas emission rates. So this plot shows some of the SO2 emissions from the Kilauea 2018 eruption measured by DOAS. And what's interesting here is that you can start to measure compare the emission rates with calculated SO2 emissions, the expected SO2 concentrations from the glass, and we can start to compare what natural samples can tell us with respect to what should be coming out of the event, what are we missing, are there extra volatile fluxes that we can't account for with the petrological models, and so forth. And so by comparing the geochemical data with these observations of gas data, we start to build a framework by which we can start to apply models in a more operational setting. So basically what we're trying to do is to look at magmatic volatiles from source to surface. Well, our starting point would be the dissolved volatile content of primary melts, which we might get from geochemical constraints such as a volatile trace element ratio. We want to understand something about the onset of deep degassing, and our volatile solubility models would suggest that CO2 is going to be the dominant driver of the onset of deep degassing, but we've seen already that sulfur may be entering the vapor phase much deeper than we expect, perhaps water as well. We want to know what the composition of the equilibrium fluid or vapor phase is and how that changes as magma ascends through the system. We want to know the dissolved volatile content of stored melts. And so this means that our volatile solubility models have to be able to account for changes in magma composition as magmas are fractionated in the system. We want to understand whether there's open or closed system degassing, and if it's an open system, what gas compositions should we be able to measure at the vent? If it's a closed system, what does the fluid accumulation mean for the priming of a magma chamber for eruption? We might want to understand something about volatile diffusion and exsolution kinetics during magma ascent. Now, lots of our volatile solubility models assume equilibrium between the vapor or the fluid and the melt at any given point in pressure, temperature, composition, space. But in a conduit, we're almost certainly looking at disequilibrium processes. So kinetics are important. And then finally, we might want to think about what free and syneruptive gas compositions and fluxes would we predict in particular scenarios, and can we measure to be able to integrate observational data with our models. So I want to make a few remarks about kind of making use of models and codes. We've just heard from some very, very fantastic new models. They look like very complicated codes to me, and I will hold my hands up and say, I'm not a coder. I don't find it very intuitive. I would like to be much better at it than I am. And so as an observational researcher, what I like is codes that are really easy to work. So we need to consider the accessibility. Accessibility is a little bit more than just who can download the source files, but that's an important aspect. Are your files open source? Can somebody get hold of them? Are there any preliminary steps that we need to take to be able to run those source files? Is there something that we need to install? Are there dependencies that we need to build? Is there a server that we need to get access to? Does the operating system matter? And all of these questions will influence how easy somebody finds it to actually work the code. And then under the lid, who can see and who can modify the underlying mass? Is this a plug and play black box kind of model? Or is this something that an observational researcher can take as a framework and modify to their particular case study? Consider the learning curve of your codes. We've heard some from at least one speaker this morning who said that their code was not particularly user-friendly, which is really good to know in advance, because then you have an idea of how much time you're going to have to input to learning this thing. Tutorials and example input and output files are hugely valuable to observational researchers who may find codes a little bit intimidating. And finally, consider the longevity of your code. We've heard a little bit about volatile calc and some of the limitations and simplifications that have gone into that code, but it has extraordinary longevity because it's just incredibly easy to use. So when you're thinking about developing a code, think about how long-lived it's going to be on a particular platform. Who's going to maintain that code? Is it going to need tweaks as the coding language undergoes evolutions? Who's going to update it as new volatile solubility models come online? I really like this XKCD comic. If you are the person down here, the random person in Nebraska that has been thanklessly maintaining the code since 2003, think about what's going to happen to your model if you should retire, or if you should get a new job and leave this particular sector of academia. It may be that you want to have a team of people maintaining this code so that it can be used by generations of volcanologists and petrologists. So once you've got over the hurdle of actually installing and figuring out what the code does, what do we want to calculate? And I'm going to show you some examples. First one is the really obvious. Let's calculate some melt volatile saturation pressures. So these are some examples that I did in volatile calc. These are from the Laki eruption in Iceland. I was using glass plus vapor bubble CO2 to calculate the saturation pressure of a suite of melt inclusions. And I also used a volatile trace element ratio, in this case CO2 niobium, to calculate the amount of CO2 that I thought had been lost from each melt inclusion, using the volatile trace element ratio as a proxy for how much CO2 this melt should have contained had no degassing taken place. And we can start then to use some assumptions and some models to think about how much gas is exsolved as a function of pressure, and how much exsolution would we expect given a particular depth of magma storage, and what might be the total emitted volatile budget of a particular eruption. So this is a fairly straightforward case of using a melt volatile saturation model. I'm guessing many of you have used lots of different models in this way. Another thing that we might want to be able to do is to calculate and compare isobars, that's contours of equal pressure, and isopleths, that's contours of constant fluid composition. And here I'm showing some data from my PhD student Melina, who's working on melt inclusions from Rabaul volcano. In these three graphs, she's used Magmasat at a constant temperature of 1000 degrees with three different starting compositions and is comparing the isobars and isopleths that Magmasat calculates. So here we've got two basalts and a basaltic andesite. And in the next slide, we've got an andesite, a dacite, and a rhyolite. And the only thing that's changing here is the starting melt composition. Everything else is the same. And if I just flick between these two slides for a while, you can see that these starting compositions do make a difference to what we think might be going on in the system, where particular inclusions are being stored. Because we know about this melt composition dependency, it becomes quite difficult to plot graphs like these that show a particular set of solubility constraints for a system. And so IAVCEI has produced some really useful ways of looking at comparing different volatile solubility models. So this one here with the blue and the red bars, these are isobars calculated for individual melt compositions in a melt inclusion suite. And we can really see how the compositional dependence, how the composition of the melt influences the saturation pressure that we get out. We can also look at comparing different solubility models, their sensitivity to pressure and temperature. Penny has talked about this in previous talks. So what IAVCEI has the great power to do, I think, is to do bulk comparisons on a single platform and a lot of batch calculations. And this is going to be really a game changer, I think, for observational researchers, because we are going to have the ability to select the most appropriate calibrations for the system of interest very quickly and easily by visually comparing the outputs of some of these codes. So I think that in terms of selecting the most appropriate model for the system of interest, we're actually making Penny, Kayla, and team have made some really, really helpful contributions just in the past few months. Another thing that we're going to want to do is to calculate open and closed system degassing paths, tracking the composition of the melt and also potentially tracking the composition of the fluid. This is some melt inclusion data from Zoltan Tarachak, who was looking at a suite of rocks from El Hierro in the Canary Islands. And he calculated these open and closed system degassing paths using decompress, which is a model that we haven't heard much about today, but he chose this specifically because it included sulfur. And what he can see here is that neither the open nor the closed system degassing pathways particularly well match his data set, but in the sulfur carbon plot on the far right, you can see that the closed system degassing pathway comes much closer to matching the observational data. And this gives us some idea about how the vapor is behaving in this system. We would also want to be able to calculate the exhaled vapor mass and the change in gas molar proportions during magma ascent. This is for the Kilauea 2018 eruption, and these authors have used a hydrogen carbon sulfur degassing model based on Gerlach 1986. So this is one of the older models. And you can see here CO2 is mostly exhaled, even from quite high pressure, whereas the water and the sulfur are starting to come out of solution much higher up in the conduit. And we can see the changing gas composition. Now, this is the kind of thing that we might want to relate to observations of passive outgassing, or pre-eruptive outgassing, it tells us something about where magmas might be being stored in the system, although with the caveats that Penny pointed out earlier, that depending on what volatile solubility model you pick, the pressure that you interpret from that may be maybe wildly different. And so picking the right model for the composition of interest is very, very important here. Another example that we haven't really looked at is trying to combine solubility models with magma ascent models. This is a model from Giuseppe La Spina, where he is using a conduit model to calculate various parameters as a magma is ascending. The bulk composition for the starting material is an alkali basalt from Etna. The model is starting at a depth of 6 kilometers, and at each increment of pressure, it is computing the gas volume fraction, the velocity of the mixture, the viscosity of the mixture, the dissolved volatile content, the temperature, and the crystal content. So this is quite a computationally expensive model, and it's integrated with melts so that at each step there's an increment of crystallization is happening, the melt composition is changing, the crystal content is changing, and the temperature is changing. To integrate a volatile solubility in this, Giuseppe has used a simple Henry's law function. So this is saying that the amount of dissolved gas is proportional to its partial pressure of the gas in equilibrium with that melt. And he's implementing it using this expression where we need a solubility coefficient and a solubility exponent. And Giuseppe was using volatile calc, a simple water versus pressure plot, and a simple pressure versus CO2 plot to calculate a curve for the particular bulk composition of interest, fit that curve and extract the solubility coefficient and the solubility exponent. And he's just doing that for the two species, effectively in isolation. And you could do this for MagmaSat or for any one of the other volatile solubility models that are out there. So this is quite elegant in that it's a very simple way of describing the volatile solubility, but it doesn't account for the changing temperature and changing melt composition along the ascent pathway. And it assumes equilibrium degassing at all points. So what about disequilibrium kinetics? When you're in a conduit, when the mixture velocity is changing very rapidly, particularly in the very upper part of the conduit. And so one of the things that observational researchers might like to be able to do is to take these equilibrium models and integrate them with some understanding of diffusion or nucleation of gas bubbles to try and understand the interplay between equilibrium and disequilibrium, exsolution and kinetics. So in terms of some future developments, what we might want to do next, we've heard this point already, but we've got a really good range of experiment compositions for solubility of pure water, and we've heard that that's not particularly sensitive to melt composition. So this seems pretty good. For CO2 and for mixed water CO2 fluids, if you're working in basalt space, you're very well served if you're working on alkaline compositions, but there are rather fewer experiments on Morb and Oib tholeiitic compositions. The closer that the experimental model matches the composition of your system, the better your outputs are going to be. So some more experiments in this compositional space would be great. Likewise, if you're working on andesites, dacites, or trachytes, there's a big gap here in compositional space where there really are no experiments. And for workers investigating volcanoes that erupt these kinds of compositions, we're doing the best we can with the models that we have available, but having models that are more tightly calibrated for these particular compositions will be really valuable. We've talked about the option of including sulfur in volatile solubility models, and it's really exciting to see the range of codes that are coming online as we speak. There are also a range of new experiments. So this is a very recent paper that's looked at sulfur solubility in I think basaltic melts. These experiments have all been done under very oxidizing conditions. Good to have experimental data. These are probably more oxidizing than we would expect to find in most terrestrial magmatic systems. Can we do these experiments under more realistic conditions for the kinds of volcanoes that we're working on? But these are producing really interesting results. So, for example, the model simulations in this paper suggest that sulfur is partitioning very strongly into water-rich exsolved fluids. And this is really valuable when we're trying to think about what sulfur ought to be doing in ascending and degassing magmas. We haven't talked at all really about chlorine in solubility experiments. And I'm not aware of any volatile solubility codes that include chlorine. So this is probably a major gap that will be very interesting to have more experimental data and more codes to help us understand how chlorine is behaving in systems. And we haven't really talked about brines at all. So I'm not aware of very many experiments or models that talk about the exsolution of high salinity supercritical fluids, nor am I aware of any models or codes that think about describing the separation of these supercritical fluids into a vapor and a brine. We also don't know much, I don't know much about the reactions between brines and sulfur-rich gases. So this seems to be an area of observational research that is only going to get bigger as we become more interested in these kinds of systems that can complex with critical metals. And that is an area where our codes might want to catch up. I've talked about the top 3 points here already, and the final one that I wanted to raise was solubility at extreme redox conditions. We've heard that a lot of the volatile solubility models available at the moment poorly report their redox, the redox conditions under which the calibration experiments were undertaken. It would be wonderful to have more tightly controlled oxidation conditions in a series of experiments so that we can understand, firstly, how terrestrial magmas are behaving as redox conditions change during degassing, and secondly, to see if we can apply some of these existing models to other rocky planets where the redox conditions are very, very different. So this is a kind of whistle-stop tour of where I think observational researchers might like to use codes. There are things I haven't touched on at all, like carbon isotopic